All right, so we're going to continue our lecture about energy transfers, work, and power. So this kind of just a review of where we left off last class. We were talking about the law of conservation of energy, that if you're in a closed, isolated system, right, no outside forces acting on it, that the energy total at any point is equal to energy total at any other point. Okay, so that's the law of conservation of energy. But now if we start considering outside forces, in other words, something's acting on the object, then there is work being done on that object. And any work done is equal to the change in energy that happens between the two different points. Okay, so that's just a basic definition of work, as it relates to total energy and stuff like that. We're going to talk about the basic definition, give you some equations for that. So we already talked about this, total energy, did that one. All right, so work is basically the transfer energy from one object to another. Notice here that the units are also joules. Energy is also in joules, and that's why it relates to one another, right? So if you lose energy, it's because you've done work on it, or you gain energy, it's because you've done work on it. The basic equation for work is equal to FD cosine theta. And what that cosine theta does is it gets the force in the direction of the motion, okay? You can only use the force that's in the direction of the motion, okay? So if I look at this example down here, the force that you're using, F, is not in the direction of the motion, right? The box is going to be sliding horizontally along the surface. So what we want to do is get the component of that force that is only in that direction. In other words, we want to get the horizontal component of that force, which is this way. And again, if you look at this, this is just a trig problem. If you do it, you're going to use a cosine to get the force here. I don't know if you remember FPX, something like that. You want the force of the pull in the x direction, okay? And that's what we're going to use. That's where you get that cosine part there, okay? And that gives you the force in the direction of the motion. D is the displacement of the box. So thinking about this, right? You know, if you have a large object, right, and you're really pushing as hard as you can, hard as you can, hard as you can, you're exerting a lot of effort, but you don't get that object to move, you've done zero work, even though you've exerted a lot of energy trying to push it, okay? So the object has to move for work to be done on it, all right? Now, if you notice there, it sneaks that change in energy also. Work is also equal to the change in energy, right? Um, so that's a basic definition here. Let's go ahead and look at a problem. It says, a box of mass m slides on a frictionless ramp of height h and an angle of 2 theta. So we're talking about this guy over here. Okay. And a separate box of mass 2m slides on a friction. Okay. Seen below. How does the work done on the boxes by Earth compare? Okay. So obviously when you release them, they're gonna travel some distance here. Okay. Looking at the work, change in energy. So think about that. I'll pause here for a second. You can pause the video to select an answer and then see if you get it correct. All right, hopefully you've unpaused it. You have an answer here. So the correct answer here is going to be B. The Earth does more work on the box with twice the mass. And why is you look at it. The basic definition here is change in energy. Well, what energy are we going to be changing? Moving the box from this height down to the ground level, this height down to the ground level. We'll be taking away potential energy. So if we look at the initial potential energy, here we have gravitational potential energies, mgh, right? So we just have m, g stays the same, and height is the same, right? The height is the same. So if I look at this, right, there's more, and we're both going to zero, right? It's sliding all the way down, so my potential energy is there. So I have 2 times, all right, the amount of potential energy over here that I'm going to lose. So the work done by Earth is 2 times as much as in the first situation. Okay. All right. Continuing on here, this is the work energy theorem. So what we have here is saying that the net work done, in other words, if you add up all the work done on an object, it's going to equal the change in kinetic energy here, right? So if we look here, let me get a different color, right? So we look here, work one, oops, net work equals change in kinetic, work one, work two, work three, all right? Kinetic energy final minus kinetic energy initial. All right, so if we look at the work done by force one, the work done by force two, the work done by force three, okay, that's going to equal the change in kinetic energy. So basically we get this equation right here. The net work done, so the work energy theorem states that the net work done is going to be equal to the change in kinetic energy. All right, now this should make sense. This is kind of common sense here. If your work is positive, that means kinetic energy is going to increase, okay? Because kinetic energy final minus kinetic energy initial, right? So to get a positive number, this has to be bigger. In other words, it has to, this has to be bigger. The final has to be bigger, so it increased. If you have negative work, okay, kinetic energy has to decrease. That means the final is going to be smaller than the initial. An example of that is like you're driving in a car and you hit the brakes. Okay, you're slowing down. You've done negative work on your car. The brakes have done negative work on your car, and your kinetic energy has decreased. Same thing with this. All right. If you have positive work, in other words, you hit the gas pedal, you speed up, you have a higher final velocity, which gives you a higher kinetic energy final, which means you've done positive work on the car. Okay. So let's see what this is. A 4-kilogram box starts with a velocity of 6 meters per second to the left. A net amount of work is done on the object now that the box is moving 4 meters per second to the right. What is the possible amount of work, possible amount of net work done on the box? All right, pause it right here. Remember that net work equals change in kinetic energy. Okay, so pause the video right here, pick an answer, and then come back and we'll do the solution together. All right, hopefully you've paused it or you've just watched straight through. So we said network. Oops, sorry. We said network equals change in kinetic energy. So I have 1/2 mv final squared minus 1/2 mv initial squared. So if I plug in here, I got 1/2 m is 4, sorry. Vf is 4 minus 1/2 4, and I got what, 6 squared. So I got my network equals, let's do it in the calculator real quick here. I got 4 times 4, 16 times 4 times 0.5 gives me 1. No, I did that wrong. 4 squared is 16. 16 times 4 equals 64 times 0.5 equals 32. So I have 32 minus 6 squared is 36 times 4 equals 144 times 0.5 equals 72. So I have 32 minus 72, which equals negative 40 joules. So the answer there is going to be, so I end up getting 32 minus 72, and I get negative 40 joules. So therefore my answer is going to be D. All right. Let's see if we got it right. Yep, D. All right, so now let's look at this graph here. Okay, so this is so like I always said, right? The first thing you want to look at when you get a graph is or what are the axes. So we have force by position. Okay, if you have a force by displacement graph, force by displacement, the area under the curve is equal to the work done. Okay, now if it's above the x-axis, this is positive. If it's below the x-axis, this is negative work. Okay, so this is just like, trying to find displacement from a velocity versus time graph. Okay, it's, you find the area under the curve, above it, it's gonna be positive, below it's gonna be negative. But this has to be a force by displacement graph, just area under the curve. Okay, so let's try this problem here. A box starts at position x equals 0 with a velocity of 5 meters per second to the right and has a net force in the horizontal direction as shown in the graph below, where the rightward force is considered positive. So the key is the box is already moving to the right, and a rightward force, in other words, with the motion, is going to be positive. All right, consider positive. At what position other than x equals 0 is the box again moving with 5 meters per second to the right? All right, so read that. Pause the video here, see if you can answer this one correctly. All right, hopefully you pause it, you got an answer here, so let's look at this. So the key to this is if we want the box to have the same velocity, right, of 5 meters per second, we need to find where the net work is equal to 0, right? Because if we find where the net work is equal to 0, that means a change in kinetic energy also equals 0, which means it's the same kinetic energy, which means the velocity has to be 5. So if I look here, this is negative work done, right? So this is going to decrease the kinetic energy. So during this time period, okay, the object, the box, is slowing down, right? Where you have a negative force acting over this displacement. So you've done negative work, so therefore the box is slowing down. So let's see here. We got a triangle. Let's find the work. So area under the graph there, what's that? -6 times 3, 18. So I got -9 joules during this time period, right? Area of a triangle. So if I look during this triangle, I got a base of 2 and a height of 4, right? So I got 8, so I have 4 joules, right? So I have +4. So I'm still down -5 joules, okay? So if I look here between 5 and 6, that's 1 times 4. So yeah, so my speed is going to be somewhere between 6 and 7 is going to get me back to the 9 joules, which gives me a 0 kinetic energy. So my answer here is going to be B. See if I'm right. Yep. There we go. All right. Perfect. All right. So now the last thing we need to talk about is what power is. So we talked about work and how it changes the energy total or transfers energy. Now power is the rate at which work is done. Okay, so there's a unit of time with this. Yeah, so power is the rate at work's done. All right, and it's the rate at which energy is transferred. So if we look at our equation here, power is equal to work divided by time. And remember, work is also equal to change in energy. So that's basically going right to these definitions, right? Um, your base unit here is going to be watts power. I mean, it's pretty straightforward. How much work did you do and in how much time? And that's how much power you've generated, okay? Oh, there you go. Units are watts, sorry. I thought I So let's look at this. A box M slides all the way down a frictionless ramp height h and an angle of 2 theta. A separate box, mass M, slides all the way down the frictionless ramp of height h and an angle of theta as seen below. How does the average power developed by the force of gravity on the box is compared for each incline. Now, it's the same picture, but notice that the masses are now the same. So remember what the definition of work was. Remember what the definition of power was. Pause the video and see if you can answer this question correctly here. Go ahead. All right. So hopefully you're back here. So let's look at this. So the definition of power, work divided by time. So let's look at this work first. So let's compare the work done. Well, the work is the same as change in energy. All right, it's going to zero potential energy, and it starts with some potential energy. UG equals mgh, UG equals mgh. So really this time, the change in energy is the same. It's going to go to zero both cases, and it starts with mgh, right? The height is the same, the mass is now the same, and gravity is the same. So it has the same amount of initial potential energy. So therefore, the work done is going to be the same. So I got the same value for both here. Now let's look at the time. Which block is going to get to the ground first? Oh, looks like common sense here that this one's going to get to the ground first in a smaller amount of time. So option one has a smaller amount of time. So you're dividing by a smaller number, thus giving you a bigger number for the power. So let's see what the answer here. The more power is developed on an incline of, so yeah. So my answer here is going to be A, I think. Let's see what happens. Yeah, perfect. So, power is pretty straightforward. All right. How fast are you doing your work? I just want to talk about this. So when you talk about power in your real life, like usually, everybody here has ridden in the car, or you have different lawnmowers with different horsepower and stuff like that. So really what we are used to power being in is horsepower, right? So, hey, my car has 190 horsepower and, whatever. So I just wanted to show you that the derivation of horsepower and how it relates to the work equation and how it relates to the power equation, and kind of give you that conversion factor, okay? So James Watt was a guy who invented the steam engine, but what he wanted to do is he wanted to come up with a way that he was able to rate the capabilities that of the engines, right? And it's the same as like cars. When you go shopping and you're comparing a couple models, you're like, oh, well, what's the horsepower? And that there you can compare, the power each car has. If that's something, especially if you're going in for like truck or hauling or stuff like that, and that is an important factor here. So how he did this was he had to come up with some way to compare it, right? So he observed his horse actually walking around like a mill, and it turned the mill as it went around the circle, right? So let's think about the forces, right? Or let's think about the variables here. Work equals force times distance, okay? So what he had to do was figure out how much force the horse had to apply, okay, to get that mill to work. So that's the first thing he did. Or, okay, the first thing he did was figure out how far probably the second thing he did. The first thing he did was figured out how far around the circle was, right? That's the distance. So he figured out, okay, the circumference of the circle that the horse walks is 75.4 feet. That gives me my distance. And he knows, then he figured out the force, right? So he said, okay, it had to pull with a force of 180 pounds to get that thing to move. So there we're able to calculate right there with just that how much work is done each time the horse makes a circle, right? It applies this force for a certain amount of time. We can figure out how much work is done each time he goes around the circle. The next thing we want to do, if we want to know power, okay, is we need a unit of time, right? So he counted how many trips the horse makes in a certain amount of time, and then he can now figure out how long it would take him to make one loop around. Using that, you can calculate the power of that horse. And that's what he did. He said force times distance, that's what we have. It required a 180-pound force, and the circle was 75.4 feet. So there's our foot-pound. This is now, it's different units here, okay? So we're calculating horsepower, okay? We're not calculating watts, all right? Then we took the work done, right, foot-pounds, divided by the time it takes to do one circle, which 60 minutes, if you did it for an hour, 144 trips. So it took 0.416 minutes to do one trip. So then we would get this, which is rounded to that, which ends up giving us, oh, I left off the conversion factor. I think it's 746 watts equal 1 horsepower. Okay, so that's the end of the lecture for that. Let's see if I can find it. Yeah, 746 watts equals 1 horsepower. Okay, so that's the end of our lecture today. We're going to get into a lab next class. I just wanted to make sure that you guys watch this. We're ready to go for next class. All right, thanks.